Hi everyone, welcome to my presentation session. I'm Prof. Changbum Chun of Sungkyunan University in Korea. Okay. The title of my talk is A General Approach for Improving the Further Iterations for the Matrix Sign Function. First of all, I'd like to outline my talk. Okay. It consists of 7 parts: introduction, a general approach for improving the further iteration. After this, I'm going to present the convergence and numerical stability analysis. And then I'm going to make some special cases from our scheme to compare the performance of our method with existing method. Okay, and then I'm going to present a numerical result to support our result. And then I'm going to end my talk with conclusions. Okay, recently, efficient computation of matrix sign function has gained significant attention, and many iteration methods have been developed, including those for the matrix sign functions. The matrix sign function was introduced by robots and applied to solving various problems in application areas. Okay, so now, developing the reliable matrix iteration method, has become an essential subject of current research. The Pade iterations are a well-known method for computing the matrix sign function. In this work, I'm going to present to you a general approach that can be used to improve the Pade. Okay, the matrix sign functions is defined like this. Okay, given a matrix A, so each matrix sign function is defined in by this formula in terms of the Jordan canonical form of G. Defined like this. So I'm going to omit the details of this one because these is very well known result in the field. Okay, so let's briefly review on some classical method for computing the matrix sign functions. Okay, the first one is Newton's method. First, let's note that matrix sign function is satisfied this matrix quadratic equations. So based on this, now we apply Newton's method to each scalar version. We got this one. Based on this, we considers each matrix version to get this one. And now here, the further families of iterations is given like this. Okay, so that's the sign function of complex number is given like this. Based on this, Kenneth and Ralph present the further iterations like this. Here, this one is LM further approximate to this function, and this one. Okay. This function has a very nice properties. These are well known, so I'm going to skip this one. And then particularly the case one gives Haley method like this. So if you want to know more on further method, please see N.G. Hyam's books. Okay, here's a motivation question for our talk. So most of the methods for matrix sign function are conjugate to the monomial of this form, C times constant times G to the power of P. Okay. So now question is, can you find a general family of methods which includes the further iterations as special cases and whose conjugation is a generalized version of this one? Okay. We need to ask this question to find more chance to have more chance to find better a method which we hope will have a better performance than further iterations. Okay, so to illustrate our approach, let's choose any one method. Okay, for example, let's consider the following 3-point method due to Wang et al. And each given like this. Okay, that is the method that contains two wave functions, pi1 and pi2. Okay, this method is known to be of order A under this condition on the weight functions. Okay, our approach is this one. Okay, let O be the conjugation of the method function of our this method of by the Mobius transformation. Okay, for the complex quadratic with this distinct roots. Given a polynomial of the form like this, okay, the question is, can we choose the wave function pi1 and pi2 in such a way that, okay, the conjugation of our method, the given method is the given polynomials in general form, F4. Okay. Apply the given method to the quadratic. We have this form map come out. Okay, if we let omega g like this and define g1 theta 1 theta 2 like this, then the rational map S6 can be transformed into this map. So this is the configuration of our map, the given map, by this Mobius map like this. Okay, for the general polynomial law of G given like this. Now we like to determine zeta 1 and zeta 2 so as to satisfy this one. The conjugation of the given map, given method is the given polynomial. Right now this one, now we have got this one. Solving this equation for zeta 2 with G1 fixed, then we have this one. So now we have a lemma. So now if we define VG like this, then it happens to be on inverse of omega of G. So based on this, if we let W rho of G like this, then W of rho, happen to be come out to be the second wave function. Here is the what we have found. Let shift your simple zero on empty function f. And suppose that x is sufficiently close to this, and pi1 and satisfy this condition, and pi2 is given by the function we just have defined. Then this method. Now notice that we just have replaced the second wave function by a new function we have found from our work. Then this method is conjugated to a general polynomial map like this, with p being any positive integer bigger than 8. 8 is the order of the given method, right here, for the complex quadratic with distinct roots. Now let's consider the matrix version of this method. It's given like this here, like this. So although various forms of the wave function pi1 are available, we restrict ourselves to pi of t for the remainder of the talk. Assuming f of x equal x squared minus identity matrix in 18 for the computation of the matrix function, then we luckily we got an explicit form of our method like this. If p equal line, the method 19 becomes like this. So if AP, that's the leading coefficient is 1, and AI equals 0 for this coefficient, then 19 method becomes this one. So this method is the Pade method of order P. So the Pade method of order P, okay, is as big as 8 are special cases of our scheme 19. Okay, so now here are our global convergence theorem and local convergence theorem and stability issue. Okay, now okay, the matrix sequence, okay, generated by our the method 19 converges to matrix function. Okay, no matter what method matrix to be used for A. Okay, here. Here's the local convergence theorem. If there exists L satisfying this one and AI equals 0, okay, before the subsequent L, the convergence rate of our the iteration is L. Okay, here. So here is the stability issue. Under the conditions of the local convergence theorem, the sequence generated by 19 is asymptotically stable, numerically stable when the leading coefficient 2 equals 1. That's our findings. Okay, here. Okay, so you can make some special select some make some selective case like this that I'm going to skip here. But for our method 19 for p equal 9 with a9 equal 1 and p11 with this condition. Now, okay, here if p equal 9, the method becomes this one. Okay, now, okay, so now we have this one. Since okay, the conjugation of this method is this one. Now we try to find uh, eight satisfying this condition for all G on the unit circle. Okay, here. Notice that beta equal 0 gives the principal Pade matrix iteration of ninth order that we call PMA9. Okay, so here's some numerical experiment on how to choose the optimal value of beta 1. Okay, so this one. So I'm going to skip this one. So the cases beta pi and beta 1.2 pi give the best result. So I'm going to denote them by OM1 and OM2. Okay, so if p equal 11 with this condition, okay, and whose leading coefficient is 1, then we have this method come out. So if we do exactly the same as the previous case, then we can show that beta 1 is 0.28 and beta 2 equal pi give the best result. So I'm going to call them okay, OM3 and OM4. So we have chosen 4 special cases of our method. Okay, so here are numerical result. So things used for numerical result is this. We used the stopping criterion like this. Okay, and we used some approximate efficient index. Okay, given like this formula. So we have compared our method, okay, with existing methods such as Newton method, Haley method, and the principal Pade iteration of order 8 to 11 that we call PM8, PM9, PM10, PM11. Okay, here. So, okay, here are the result of average number of iterations over 50 randomly generated matrices for each matrix size. Okay, here, and each of this method here. Okay, if we look at into this table, you can see that our method OM1 is the takes the least number of iteration for convergence on average, followed by our next method OM4. Also, we measured the average CPU time for the same experiment. Okay, then notice that our method OM1 is the fastest. Okay, on average, and OM4 is followed by this. And notice that our method, these two, are twice as fast as this further iterations of the same order. Okay, now we can compute the average efficiency index here, and approximate efficiency index based on this one. Okay, here's the result for okay. So now this one. To compute this average efficiency index, we need to compute D. Okay, so to compute this one, okay, we assume the the value of D for PMA is S. So now we can assume that the other method are have a linear relation with this method. Okay, so by using the least square method, we can compute D. So based on this computation, we can compute the approximate efficient index like this. Okay, so here is our numerical result for approximate efficient index for each value of S and each of the method here. Again, okay, if you look into this table, you can see that our method OM1 is what most efficient. Okay, even on average. Okay, and the next followed by OM3, this one, and then OM1 and OM4 are also more efficient for large values of S. Okay, here. So from this table, you can plot this one as a bar graph like this here. Yeah. So OM1 is this one. So this horizontal axis is for values of S, and the vertical axis is for approximate efficiency index. So you can see that our method OM1 and OM4 are higher than the further method. Okay, for particularly for large values of S. Okay, so let's make conclusions here. We have presented an approach for improving the Pade iteration. This approach is a method global convergent, stable, and can have any positive order. The method present improved Pade iterations in terms of CPU time and the average number of iterations over 50 randomly generated matrices for several matrices. In terms of the approximate efficiency index, our method have higher values than those of existing method. Okay, particularly when a high number of iterations is required. Although interested with an ace of the method, our approach can be applied with any other method of any order to improve for the iteration. That's why we called our approach is a general approach for improving this one. Okay. Thank you for your attention. Okay, that's what you have today.